Hi everyone, today we are going to go through periodicity, and what periodicity is a look at the trends on the periodic table. So back in the day when the periodic table was arranged, it was arranged by certain characteristics. Those characteristics have changed just a tiny bit, but when Mendeleev was creating the very first periodic table, he created it based on the patterns that he saw within the elements, and we still see those same exact patterns today. So giving you a little bit more of a background on the periodic table. First thing that we're going to do is we're going to watch this quick video about alkali metals and water. And what I would like for you to do is I would like for you to answer these questions. Which elements are most reactive? And what is the periodic trend? Meaning, what is the trend of reactivity as you go down a group in the periodic table? How do you think elements on the periodic table are organized? And is there a specific order?
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
Now, 2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! Wow, that is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason they wouldn't let us have any of that. So there you go. Today's lesson:
Never mixed alkali metals with water.
Now let's see another reaction of the alkaline metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
So go ahead and answer these questions. Which elements are you going to see that are going to be the most reactive in the periodic table? Are they the ones that are going to be on the top, or are they the ones that are going to be on the bottom of the group? Next, how do you think the elements on the periodic table are organized? And you might remember from your periodic table web quest, you might remember the answer to these questions. So Dmitry Mendeleev actually is credited with being the creator of the periodic table. And in 1869, he became a chemistry professor. He actually was planning on going to medical school, but ended up being turned down from medical school, and he became a chemistry professor. And in his research, he ended up recognizing that there were trends within the different elements. And so if he organized those elements in a certain way, then it kind of made a little bit more sense. Now, understand that if you were to go and do a Google search real quick for periodic table versions or versions of the periodic table, you're going to find circle diagrams. You're going to find all kinds of random diagrams. I used to work in downtown La Jolla in a restaurant, and there was a gentleman who used to come in, Dr. Kohler, and Dr. Kohler came in with a briefcase one day and he said, look, I'm reorganizing the periodic table and everyone's going to start using my periodic table. And that was in the early 2000s. So people are always looking at ways to restructure and reorganize the periodic table in ways that make sense. So some people organize the periodic table in their research based on what they believe show patterns that would cause things to be carcinogens or whatever. And that's actually what Dr. Kohler was working on. So the periodic table that we use in class is the periodic table created by Mendeleev with a couple of adjustments. So he organized his periodic table based on reactivity and atomic weight of each element. But we have actually shifted that. And if you look right in the transition metals right around iron, you'll see that the atomic weight is no longer the determining factor. We actually organize our periodic table by atomic number and reactivity. So notice the difference there. It's no longer organized by atomic weight, it's now organized by atomic number. So the periodic table, and you did this in your periodic table web quest, so I'm going to go through this pretty quickly. Your periods are your horizontal rows. As you go down, what we've learned is as you go down into another row, you go into another energy level. And then the groups are also called families, but we usually use group naming, and they are numbered. They're numbered either in Roman numerals or they're numbered just straight across. The Roman numeral numbers help us, if you recall from our last lesson, by helping us identify what our valence electrons are. Elements in the same family or the same group have similar physical and chemical properties. Reactivity, hopefully you noticed, increases as you go down a group on a periodic table. So you have your group A elements, which are your representative elements, and your group B elements, which are your transition elements and your intertransition. So if you look on the periodic table, the lifted up elements are your group A elements, and then the transition is where you're transitioning from the left side to the right side of the periodic table. So metals make up 80% of the periodic table. They conduct electricity very well. Go ahead and look up what is the best conductor of electricity. I think it would really surprise you. But most people think copper. It's actually not copper. It's actually silver. Silver is going to be your best conductor. But we obviously don't use silver to wire our homes because it's very expensive. So metals are highly conductive. They're really lustrous, which means that they're really shiny when they're cleaned, but you have to clean them really well. They're ductile, which allows them to be drawn into a wire. That bulk property of metals ends up allowing us to, we have that metal, and so we draw it into wires and we wire our whole home, and then that ends up getting us electricity throughout our house. So that's a property of metals that is really important. They're malleable. They can be pounded into a sheet, into very thin sheets. Think about siding on buildings. Think about cars, cars that were made out of metals. Think about just simply aluminum foil. Those are examples of metals that have been pounded into sheets, okay? And then also they are solid at room temperature with the exception of mercury. Alkali metals are in group 1. Alkaline earth metals are in group 2. Then you have your transition metals. Your transition metals transition from the left side to the right side of the periodic table. And your inner transition metals, which are down at the very bottom. If you remember, they're called the lanthanides and the actinides. We also call those the inner transition metals. Then we have metalloids. Metalloids are those stair steps. So we have the stair step that separates the metals from the nonmetals. They have properties, the metalloids that touch that line have properties of both metals and nonmetals. For example, silicon and germanium are used in computer chips. We also have solar, and they're also used in solar cells. Nonmetals. Nonmetals are not shiny, and they're really bad conductors of electricity. So these properties, you're going to, if you are going to be looking for different materials to build an airplane or to build a device, if you want that device to absorb energy because you want it to be able to heat things up, you're going to go with a metal. If you want something that's going to keep the energy out, it's not going to take in that energy, you're going to want something that's going to be non-metal, something that's not going to conduct that energy, okay? Some are gases at room temperature, and some are brittle solids like sulfur. So the gases would be like oxygen, chlorine. Most of, all of your noble gases, those are gases. A lot of your nonmetals are gases at room temperature. Halogens make up group 7A, chlorine, bromine, iodine, fluorine. And then noble gases are typically going to not be reactive. Neon, xenon, helium, those are going to be your examples of your noble gases. And they're not reactive because they're super stable. So answer some questions for me. Which is more reactive, nitrogen or phosphorus, and how do you know? And which of the following is going to be larger, oxygen or oxygen with a 2- charge? That one is more of a guess. What do you think that the answer is going to be? So oxygen, okay, and then I have O with a 2-, I gained 2 electrons. So do you think that that atom is going to be bigger or smaller? The ion, do you think the ion is going to be bigger or smaller than the standard neutral element of oxygen? Periodic trends. For your periodic trends, so going into these periodic trends, the trends that we see, first off, electron configurations. Electron configurations are going to end the same in each group. So group 1 will end in S1, group 2 will end in S2, group 3A will end in S2P1, and so on and so forth. Now, atomic size. I really like atomic size. It's one of the most important ones because it's a trend that's very unexpected. And something that I really like about the Bozeman video that I'm about ready to show you is he really talks about the electric charge. So what ends up happening with atomic size, as you go down the groups on the periodic table, you're adding an energy level. So you're getting your electrons farther and farther and farther. It makes sense. Going from top to bottom, you're actually going to increase in your size, okay? But here's the kicker. As you go, and hopefully you learned this in your lab that you just did, but as you go from left to right, you're adding charge in the center, but you're also adding charge in the outside. And what we've learned is we've learned this law. It's called Coulomb's law. And Coulomb's law tells us that our force, our electrostatic force, is going to be equivalent to K, which is a constant, times Q1 times Q2 over R squared. So what ends up happening is I've increased that charge. I've increased that numerator, but I have not changed my radius. I've not changed my radius at all because I'm adding those electrons to the same exact energy level. So since I haven't changed my radius, what ends up happening is my force ends up going up. Since my force ends up going up, it causes the atom to pull in. So as you go from left to right on the periodic table, you actually decrease in size. Most people will tell me when they are doing practice problems, they'll say, oh, you've got a typo here. You're actually getting bigger as you go from left to right, but that's not true. You're actually decreasing in your atomic size as you go from left to right in the same exact period, in the same exact energy level. Another trend would be ionization energy. So ionization energy is the energy that's required to overcome the attraction of the nuclear charge. What does that mean? Like in layman's term, how much energy is required to remove an electron? Okay, how much energy is required to remove an electron? Well, think about it this way. If you've got fluorine is like going to be super small. Okay, fluorine's going to be super small. And then you've got something over on the other side of the periodic table, and that's maybe going to be a lot bigger. Which one is going to be easier to remove an electron from? Well, right here with your bigger element, it's not going to be as difficult because you're like pulling off from the edges of something. You're chipping away at it, right? Whereas with fluorine is holding on to those electrons really strong because you have a really high electrostatic charge in general. So the ionization energy for fluorine is going to be much higher than the ionization energy for, say, francium, which is at the bottom. It's going to be your bigger element. It's going to be a lot easier to remove an electron. So ionization energy increases as you go from the bottom to the top and increases as you go from the left to the right. So you have an increase in ionization energy that way. Ionic radius. Here's another one that is kind of interesting. So with ionic radius, what ends up happening is, say I have something like sodium, and sodium tends to lose an electron. So look at it this way. The last time you went to Disneyland, maybe you went with a group of people. So you're walking down Main Street. Main Street is super busy. I mean, come on. Don't we all miss Disneyland? But so what happens is you're walking down and you've got like mother hen in the center. And you've got 5 electrons on one side and 5 electrons on another, okay? Or how sodium is. Sodium maybe has 5 electrons on one side and 6 electrons on the other. So you've got this long chain. Well, someone comes up and takes one of those kids, okay? Which is drastic and crazy. So what's sodium going to do? Well, the mother hen is going to pull everyone in closer because mother hen wants to protect everybody around them, right? And so sodium, as sodium becomes an ion, it loses an electron to become Na+. And what happens when sodium does that is sodium actually gets smaller in size. It gets smaller in size, again, because you're dealing with that electrostatic charge as well. So you're going to end up pulling in closer. Sodium is going to get smaller. Whereas chlorine's hanging out over here, and chlorine has its electrons. So you've got, electrons here and electrons there. And then all of a sudden someone's like, hey, I want to go hang out with that family. And now they add to the family. And so why is mother hen not going to be worried? Well, because if someone gets picked up, it's going to be someone from another family, right? So if someone gets taken, it's going to be someone from another family. So chlorine's not going to worry about anyone as much. And so therefore, chlorine with a -1 charge is larger. So as you go from neutral to an anion, because you've gained an electron, you get larger. As you go from neutral to cation, which is positive because you've lost an electron, you actually get smaller. And that's the periodic trend for ionic radius. Electronegativity. Electronegativity is also important because electronegativity is really what determines a lot of reactivity. Electronegativity is an atom's tendency to attract electrons when they are chemically combined with other atoms. Okay, so when they're chemically combined, what is going to happen? Like, are those, and what electronegativity does is it determines what type of bond is there. And that's actually what we're going to look at in a few weeks. But you've got these electrons, and the electrons are either going to be shared, or they're going to be given up from one, or they're going to be taken by another one. Something that has a high electronegativity is going to take everybody's electrons. Something with a low electronegativity is going to give up electrons. And something like two things that have very similar electronegativity, guess what? Similar strengths, similar personalities, they're going to end up sharing really nicely. So are your electrons going to be evenly shared? Is one going to pull more, or is the other one going to just give up and just not even try? Okay, so electronegativity increases as you go up a group from bottom to top and increases from left to right. So it actually follows the same trend as ionization energy, because it takes more energy to turn something into an ion if it's got a high electronegativity, right? Because it's going to hold on to those electrons really tight. I look at it this way. This is like your Simpsons. Like you've got your Nelson, which is your big bully on the playground, and then you've got Flanders kids. So Flanders kids are down here, and they're just like, "Here, take my candy," and Nelson's over here, and Nelson's like, "Give me all your candy." And that's actually how I look at electronegativity. Electronegativity, higher electronegativity, going to take everyone's candy. Low, very, very low electronegativity is not going to defend themselves. Metallic character. So metallic character is another trend that we're looking at. Basically, how closely does an atom or an element behave like a metal with metal characteristics, which kind of relates to the desire to lose electrons. Now think about it this way. Where are most of your metals? Most of your metals are over to the left, okay? And then you're going to increase, so your metallic character is going to increase this way. It's going to be opposite of ionization energy. On the periodic table, metallic character of the atoms increases down a family or down a group and decreases from the left to the right, meaning it increases from the right to the left.
And this is Chemistry Essentials Video 6. It's on periodicity. In other words, it's going to be the patterns that we see in the periodic table. Now, what determines that is going to be electron configuration. And we configure that out using the Aufbau principle, which is actually German, and it means the principle of building up. So we're building up from lower to higher energy levels. And so what we can find is these trends that start to emerge. But it's most important, instead of just memorizing them, that you really understand what's going on inside the atom that determines those trends. And so periodicity, remember, is going to be derived from the electron configuration. In other words, where the electrons are. We can determine that by using the Aufbau principle. And if you were to watch the last video on electron configuration, I think that'd help a lot. But what's the meaning behind this? It all comes from Coulomb's law, which helps to explain electron configuration. And also helps to explain these trends. It explains changes in the ionization energy, changes in the atomic and ionic radii, how big the atom or ion is, electronegativity, and finally the ion charge. And so if you really understand Coulomb's law, you can kind of work your way through this on the periodic table. Why is this important? We can use the periodic table to make predictions, especially about things that we haven't even designed yet. And so if we look at the periodic table, this on the right side is going to show us which of these are going to be filled over time. But if you look at the periodic table, we'll find trends. And so here's hydrogen. What we really need to do is take helium and then put it over in this S block. It's going to make us, it's a little easier to understand. And so what we're going to have are energy shells, and then these would be subshells within that. And so one thing you should understand about the periodic table is that this F block should slide right in here. It'd be hard to write a convenient periodic table, but that's really how it should be set up. Generally, we've just put it down below. And so what's guiding this or explaining the electron configuration, remember, is Coulomb's law. And so it's pretty simple. If we look at the protons on the inside of the nucleus, they have a positive charge. The electrons have a negative charge. And so Coulomb's law says we just multiply those. In other words, the bigger they are, the bigger the force between the two is going to be. But as we increase the radius, the distance between the nucleus and those electrons, then we're going to see a decrease in that force. The one thing that you have to add to that is that once we fill up one of these orbitals or subshells, it's going to shield the electrons on the outside from those on the inside. So let's get started and work through this list. What's going to happen to the ionization energy? Well, let's look at Coulomb's law. Ionization energy is the energy required to pull one of these electrons away. And so what's going to happen as we increase the size of atoms, we're going to increase the number of protons, and so we're going to make it harder for you to pull an electron away. And so we move across the periodic table, we're going to see an increase in ionization energy. What's going to happen as we go down the periodic table? Well, as we go down the periodic table, they're getting bigger and bigger and bigger, and so the radius is going to get larger. And so therefore, we're going to see a decrease in ionization energy. So you can think of ionization energy going up and to the right. Now, it's not as simple as this. What we're really looking at is within subshells, we're going to see that pattern because you'll see changes within here and orbitals as well. But it's just a general trend, and it comes from Coulomb's law. Let's look at atomic and ionic radii. Well, what happens as we increase the atomic number? We're increasing the number of protons. What is that going to do? It's going to pull it in. In other words, it's going to pull those electrons more closely to the center. And so it's actually going to be the opposite. It's going to increase as we go down, and it's going to increase as we go from the right to the left across the periodic table. And so you can see this graph of atomic radii is actually going to be the inverse of what we saw with ionization energy. What about electronegativity? Electronegativity is how much an electron, and it's bad to say this, but wants an electron. In other words, how much it would like to receive another electron. Well, remember, as we're going across a subshell, let's say we're going across this P block right here, as we go across, we're increasing the number of protons, and therefore we're increasing that pull of the nucleus on the electrons outside it. And so as we move from the left to the right, we're going to increase how much that atom wants an electron, at least until we get to the noble gases. And so electronegativity is going to follow ionization energy as well. What if we look at then ionic charge? Well, to look at ionic charge, we really have to look at how close an atom is to a noble gas. And so let's throw noble gases up here. Noble gases are going to have a full inner electron subshell. And so anything that moves you towards that is going to make you a more stable atom. And so remember, the only atoms that exist by themselves are going to be the noble gases up here. So a quick way to figure out ionic charge using Coulomb's law is to just look how close you are to a noble gas. And so let's look at the halogens, which are right here. How many electrons would halogens have to get in order for them to move to a noble gas? Well, just one electron. And so they're going to have, in general, a -1 charge. Let's move over. These would have -2, -3. Let's go way to the other side with the alkali metals. What about them? Well, it would be hard to go all the way across here to get to the noble gases. It's just easier to go around the back. In other words, they could lose the electron, and when you lose the electron, you have a +1 charge. And so we could kind of work it up in this direction as well. And so again, it's not hold fast. In other words, these are general trends, but they can all be predicted just by applying Coulomb's law. So it's hard to talk about the periodic table without talking about Dmitri Mendeleev, who's really the father of the periodic table. But you've probably never heard of Julius von Meyer, who was a German who was working on the periodic table at the same time and published his periodic table around the same time as Mendeleev. Now, why haven't you heard of Meyer? Well, Mendeleev made these huge predictions. In other words, here's his periodic table. Then you see here that he had some question marks where they hadn't identified those atoms. What he did is he would predict them. And so he predicted germanium, and he called it ecosilicon. And here are all the predictions he made about the properties of this ecosilicon. And if we look at his predictions and then compare it to the actual values all the way down, you'll find that he was pretty much spot on. And that's why Mendeleev is given credit for the periodic table. Not only was he able to build it, put it together, but he also made these great predictions, and his predictions were spot on. And so that kind of lends to this next topic I wanted to talk about, which is material design. What we can do is we can take things off the periodic table. So let me grab some atoms. Let me grab some silicon and some oxygen, and so we make some silicon dioxide. And when we do that, we get a ceramic. A ceramic is going to be build up maybe stoneware or earthenware. So it's going to build up these tiles over here on the side. And so if silicon dioxide can make that, well, what about something below that? What about tin? If I were to grab that, I could say maybe those are going to form ceramics, and they will. They'll form glazes that are going to be on these ceramic tiles as well. And so what scientists can do is they can dance around the periodic table, and if you know some of these trends, you can make predictions about new materials. And so again, in summary, periodicity comes from the electron configuration, which is determined by the Aufbau principle. But what really explains it is Coulomb's law, which allows us to make these big predictions. Ionization, remember, goes up and to the right. Atomic radii increases down and to the left. Electronegativity up and to the right. And then ionic charge, remember, we find where the noble gases are, and then we look at how many electrons we have to gain or lose to get there. And then these are important in designing materials. So you should have learned to predict or justify trends in atomic properties. Where would I point you if you didn't get that? Remember looking at this chart and seeing how ionization and electronegativity change. If we were to look at justifying the arrangement based on reactivity, it all goes back to Coulomb's law. And remember, the bigger the charges are, the bigger the ionization energy, or the bigger the force holding the electrons in place is going to be. There's also the shielding effect. And then remember, we can identify